is Samar Shaukat. I have to present the topic Kaons production in Proton Proton collision, a study of jet and energy dependence at LHC, under the supervision of Dr. Ali Zaman. So here is the outlines. First of all, we discuss about the introduction. In introduction, we will go through discuss about the standard model and the fundamental forces. Then we will move on towards the charged particles, specifically Kaons particles production. And in literature review, we will discuss the charged particle production mechanism and jet production in HIJING model. And methodology, we will discuss and simulate the HIJING model, and then we will analyze our data and visualize. And lastly, we will see our results and discussion. In results and discussion, we will mainly see our topics like multiplicity, pseudo rapidity, and transverse momentum. And at the end, in conclusion, we will see some key findings and discuss some future research directions. So here is the introduction. First of all, we discuss about the standard model. What is standard model is basically the fundamental particles, framework of fundamental particles in which we deal with the fundamental particles and the forces of the universe. Like here you can see is our the total standard model having 6 quarks and 6 leptons, and these are basically the four force carriers. Now the fundamental forces, and we have overall four fundamental forces in our nature. First of all is the gravitational force, which is the weakest force in the all forces, and the range of this force is very long, and this force is governs between the planets and stars. And this force is negligible at particle level. Also the electromagnetic force, this is also infinite, very long range, and somehow less shorter than gravitational force. It is also infinite in nature. Now move on towards the strong nuclear force, which binds the quarks together like in proton and neutron, and this is strong force, and this is very short range. Also the weak nuclear force, which is responsible for the radioactive decay. The Large Hadron Collider (LHC), basically the Large Hadron Collider is the most powerful accelerator in the world, having a circumference of 27 kilometers and 17 miles, which is located in the France-Swiss border. At LHC, we will accelerate the proton beams nearly close to the speed of light, 99.9% approximately, and yet achieve the maximum energy is 13 teraelectron volt, which are recreating the conditions of Big Bang. And in every second, basically, collisions produce 600 millions of particles interaction, and annually it produces 30 petabytes of data. And proton beams are gonna smashes at four detectors, which are named as CMS, LS, L plus, and LSCP. We are working on LS and the LS experiment here, and LS stands for a Large Hadron Collider experiment, which is a dedicated heavy ion collider. It is also used to study, optimized for the study of quark gluon plasma. We will also study heavy ion collisions as well as proton proton collisions, specifically what we are doing in our research right now. And we will investigate the whole dense matter and study the parameters like multiplicity and charged particle production. Now the charged particle production, in charged particle production such as proton and neutrons, which produce at the high energy collision at LHC, and we discuss the parameters like multiplicity, which is the total number of charged particles produced in the collision event, and the pseudo rapidity, which is the angle of particles emission relative to the beam axis, and which is important for understanding the angular distribution of particles. Here is the relation of the pseudo rapidity, eta equals to minus ln of tan theta by 2. Any transverse momentum, which is the momentum of a particle perpendicular to the beam line, and transverse momentum, this is very crucial for jet formation. Here is the Kaons particle. Some properties here we can see that it is from meson boson. You can say specifically the quark contents are up and anti strange US bar, and the charged electric charge is +1 e, and the spin is 0, parity is -1, the strangeness number of this particle is +1, baryon number and the lepton number is 0. Because this is a strange particle, it is massive. You can see here the mass of the kaons is 493, and that's all. Here is the charged particle production mechanism. There is two types of scattering: hard scattering and soft scattering. In hard scattering, basically high momentum transfer between quarks and gluons, which leads to the jet formation. And in soft scattering, basically low momentum transfer and low energetic particles mainly produce, and which contributes to the multiplicity. And in our research, we will specifically correlate the relation between the collision energy and the particles production, focuses on the jets. And here is jets. What are jets? Jets are basically sprays of particles resulting from the hydronization of quarks and gluons. Basically, jets serve a crucial role for understanding the strong force, and we will easily understand and see the insights of the initial state as well as the dynamics of the final states after the collision at LHC. We are using the HIJING model. What is meant by HIJING? HIJING means the heavy ion jet interaction generator, which is a Monte Carlo event generator in which we can simulate PP and as well as heavy ions. Why HIJING? Because HIJING model is very crucial for understanding the quark and gluon breakup, and we will also simulate soft processes, low energy interaction, and we will also see the hard processes, which is high energy interactions. And in our scenario, we are using HIJING in our research to simulate proton-proton collision and analyze the data for the production of charged particles and see their types like multiplicity, pseudo rapidity, and transverse momentum. Here is the methodology and simulation with HIJING. We are going to investigate the charged particle production at different energies like 0.9, 2.76, 5.02, 7, and the max 13 tera-electron volt using the HIJING model, and we set the center of mass energies, and we are using the collision system Proton Proton, and we then set the number of events for statistical significance. And last, we will book the histograms for multiplicity, pseudo rapidity, and transverse momentum. And also, we see where is the jet values like 0, jet off, jet on 1 and 2, and study the multiplicity, which is the total number of charged particles, pseudo rapidity, angular distribution of the charged particle, and the transverse momentum, which is the momentum of charged particle perpendicular to the beam axis. Now, here are our results and discussions. Here is the multiplicity results in proton-proton collision. We are using five different energies: 0.9, 2.76, and 5.02 tera-electron volt is here right now. And on x-axis we have the multiplicity, and on y-axis we have the probability of the charged particle production. As you can see, mm, the events with fewer particles are more frequent, because here you can see at the low value of the multiplicity there is more probability of the production of charged particles. But as you can increase the multiplicity, what you can see is the distribution shows a steeper fall. It means overall Kaon's yield is low. Also, with the varying the amount of energy, like here is 0.9. If you increase the energy up to 0.76, what you will see that as the collision energy increases, the peak shift towards the higher multiplicity, which basically suggests that average particle production is now more. Also, the distribution becomes more broader and smoother. So the particle production is more as you increase the energy, and also the probability of the production of fewer particles is more. Similarly, at 5.02, again you will see a wider and the higher particle yield observed, which indicates more particle produced at higher energies. Now let's check the jet dependence. As you can see here, constantly the at jet 0, which is meant by jet off. When jet is set as off, you will see less frequent particles are produced, and when jet is set as 1, the intermediate behavior, and when jet is 2, you can see the highest peak in all the given energies. So uh, jet 2 is more prominent than jet 1, and last jet 2, which decrease sharply at the larger multiplicities. Similarly, the same multiplicity results at 7 and 13 makes their electron volts at 17. We will again see the distribution tail now extends more further with higher energies, which also basically shows higher multiplicity events become more likely as the collision energy increases. And also again the jet 2 is more prominent, and again the highest peak than jet 1, and jet 0 is again uh, remains at lowest, and jet 2 dominates across all the multiplicities. And at 13 electron volt we got some irregular with wider fluctuations, which basically shows due to the effect of using extreme energy, and at extreme energy we are unable to simulate the more number of events. That's why we use just 600 events here, and that's why some errors are more in this graph. So the conclusion is that as the energy increases, Kaon multiplicity broaden, and again the particles production is more, and jet 2 constantly dominates than jet 1, and jet 0 always remains the lowest. Now the pseudo rapidity results in proton proton collision. Here you can see on x-axis is basically the eta pseudo rapidity, and on y-axis is basically the probability. And here in this slide we have three energies: 0.9, 2.76, and 5.02 tera electron volt. So at 0.9 tera electron volts, here you can see the pseudo rapidity results. The plot demonstrate that most of the particles in the proton proton collision concentrated at the central region is symmetric. You can see the forward and the backward, and at the central region at 0, the most of the particles is at concentrated at the center at eta equals to 0, and it decreases with increasing eta mod. It means in forward and the backward region the production of the charged particle is less. It means higher yield will be concentrated in the central region. And as you increase the energy, you can see here the peaks become more pronounced and more broader, which indicates that the production, here you can see peak up to 0.24, and here you can see peak up to 0.32. It means, which indicates that the increase in the average Kaons production. And also you can see at 5.02 again the peak is now more broader and more prominent and more pronounced, which indicates the production now increase. So by increasing the energy, the production of the kaons also increases with more broader values. And let's now check the jet dependence. As you can see, again the at jet 0, when jet is set as off, there is less dense particles produced, and you can see which is not prominent, and then jet 1, and the most peak value we got when we jet as set as 2. So the most particles produced when we set as jet 2, and also you can see the particles is more compressed in compressed region when our jet is set as 2, because you can see our peak is compressed, and when it's set as 0 or 1, the peak is not so much compressed as compared to jet 2. So what does it mean? It means that more particles produced in the central region whenever jet is off, jet 0. Okay. So again, here is the pseudo-repetitive results for the 7 tera electron volt and the max 13 tera electron volts. Again, by increasing the cool energy, what we got is that we got the more sharper and taller peak in the forward and in the backward region. Again, you can see here whenever jet is 2, we got more centered particles produced in the forward and the backward region, and more dense particles. And when the jet is 0, so we get less dense particles produced. And also we got the pronounced production of particles. And at last, at 13, the max energy, again we got some irregular fluctuations at the mid. Why? Because at higher energies we are unable to simulate the more number of events. We just simulate 600 events here. That's why we got some errors and statistical fluctuations in this graph. But the thing is that we got prominent broader peak as compared to previous. So what we conclude is that as the energy increases, the Kaon productions also increases with wider peak. Now let's discuss the transverse momentum results in proton-proton collision. What you can see here is at 0.9, 2.76 and 5.02 tera electron volt. The spectra here you can see decreases rapidly with increasing PT. As you increase the value of PT on x-axis, we having PT in giga electron volts per C, and on y-axis basically the probability. So as the PT value increases, what you can see here, you are see a rapid decay. So what it indicates that low momentum particles, here you can see 0 between 2, low momentum particles are more common, or you can say more frequent than high momentum particles, because here you can see that the frequent of the high momentum particle is less as compared to the low momentum particles which are producing more. So also low momentum particles also produces at low PT transverse momentum, and because the transverse momentum particles are high PT particles, that's why they are producing here. So now what if you increase the energy? So here energy is 2.76 tera electron volts. So as the energy increases, what you can see here is that you got a longer tail, and your particles now also goes to high PT. Now here you can see the particle production up to 10 or 12, but what you can see here, it goes up to 12, 12 up to 16. So it means high PT particles are also now producing. By how? By increasing the amount of energy, so you can easily produce the high momentum particles, high PT particles. But at low energies, only low momentum particles are more frequent, and also the tails extends to the high value. And again at 5.02, you can see it will goes more on the right side. So it means high momentum particles are also now producing more. Now let's compare the jet dependence. Again, you can see the jet 0 has the lowest yield in as well. The jet 1 is intermediate, and jet 2 is now again dominate jet 1 and jet 0. What does it mean? It means that whenever your jet is on, it produces high momentum particles. Because jets are high PT particles, that's why whenever jet is on, either 1 or 2, it produces high momentum particles. That's why you can see this blue and red high momentum particles are producing as compared to jet off. It only produces low momentum particles. Now here is the transverse momentum at 7 and 13 max tera electron volt. Again, what you can see here, the production of high momentum particles now exceeds up to 16. It means now more high momentum particles are now producing at 7 tera electron volts. Again, jet 2 dominates and jet 0 has the lowest yield. Why? Because jet off, and whenever jet is off, there is production of only low momentum particles, and low momentum particles are frequent here. And at last, 13 tera electron volts. Again, we have some irregular fluctuations here. Why? Because our events are less due to at higher energies we are unable to simulate more number of events. That's why we have got some errors in simulation. But the thing is that we got the same, but the parameters are similar. That the Jet 2 dominates and the Jet 0 has the lowest yield. So what we conclude here is that by increasing the energy, we got the broader and the flat uh, spectra, which means shows the Kaon productions extend towards higher momentum, and the production of Kaon particles is more, and the high momentum particles are produced as you increase the collision energies. So here is the conclusion after simulating Kaon's particles at different LHC energies and study their parameters. We got these conclusions that Kaon's production increases with the collision energies, which shows enhanced particle yield at higher tera electron volt levels. So as you increase the collision energy, you can easily produce the more kaons. Also, the multiplicity distribution broader and extend, which indicates more active Proton interaction at higher energies. Also, the pseudo rapidity plot with double symmetric becomes wider and taller with increasing energies. Similarly, the transverse momentum spectra flatter, which indicates that stronger production of high PT particles, high PT kaons, you can say specifically. And the thing is that jet dependence is consistently across all results. Jet 2 dominates and followed by Jet 1, and Jet 2 has the lowest yield in all the parameters. Here is the future work. We will set different. We will check our by using different jet values, and then we will compare collision comparison. We will use proton nucleus. We will use different collision systems like proton nucleus and nucleus nucleus. We will also explore the future LHC upgrades. If there is any upgrade in the energy, we will definitely use that energy and simulate for that. In future, we will also use some advanced models, sophisticated simulation models, and at last, we will also correlate our simulation with the experimental results of Alice and validate our model. Acknowledgement thanks to our supervisor, Dr. Ali Zaman, for his valuable guidelines, and our program in charge, Dr. Yasir Ali, for his valuable counseling and support, and our fellows and students and family and friends. Here are the reference of context. Thanks. We are sincerely appreciate your time and attention. We are grateful for the opportunity to present our work, and we are welcome any question or feedback.